Hello everyone. This is a quick video to give you a worked example of a problem involving Charles' law. Now, Charles' law was devised by a French hot air balloonist called Jacques Charles, and Jacques Charles figured out, partly through his experiments with hot air balloons, that as the temperature of a gas increases, the volume also increases. So those two quantities are directly proportional. As one increases, the other decreases, and vice versa. So the equation that we use for that is V1 over T1 equals V2 over T2. And just like in the last example with Boyle's law, I'm going to insist as you're learning this that you use this method and plan everything out before you start the problem. I'm going to do it a little bit differently here only because I'm going to need a little extra room to make some conversions. Now, the other important thing to remember is that the temperature must be in Kelvin. Always, always, always. So if you're given a temperature in Kelvin, and it will have the abbreviation K after it, consider that a gift from the heavens, because often we talk about temperature in terms of units that normal people typically use, like Fahrenheit or Celsius. Believe it or not, in most areas of the world, you're going to hear about temperatures in Celsius rather than Fahrenheit. So we're going to get used to using this and the Kelvin scale in these problems. Every single time you do a gas laws problem, you should first convert your temperatures to Kelvin. So without further ado, let's go ahead and break down this problem. So 600 milliliters of air is at 20 degrees Celsius. So that first part gives us our initial conditions, our V1 and our T1. Now this is, so we start with 600 milliliters. Again, a milliliter is a unit of volume, so that will be our V1. We don't need to convert this at all, again, with volume, as long as the units are the same on both sides, unless they ask you for a different unit, then you're going to be good using whatever units they give you. So we're not going to fight that, and we're going to go ahead and put that in exactly as it's written. For sig fig reasons, we need to make sure we do that. So then we're going to figure out what 20 degrees Celsius is in Kelvin. And the way we do that is very, very simple. We take the temperature in degrees Celsius, and we just add 273. So 20 plus 273 is equal to 293 Kelvin. That's a temperature that you'll typically see a lot. 20 degrees Celsius is about 68 degrees Fahrenheit, which is typical room temperature. So the temperature in the room you're in right now is likely something close to 20 degrees Celsius. So moving on, we have the second part of our problem, and it asks what is the volume. So clearly here, we're solving for V2. We don't know what the second volume, what the final volume of this gas is, but we do know that we're heating up the gas to 60 degrees Celsius. So we're going to take that 60, we're going to add 273, and we're going to end up with 333 Kelvin, a nice round number there. So these are the numbers that we're going to plug into our equation, and then we're going to solve. And if we have a proportion here, two fractions, we're going to have to cross multiply to solve for whatever the unknown variable is. In this case, we're solving for V2. So let's go ahead and plug in these numbers and see where we're at. So 600 divided by 293 is equal to V2 divided by 333. So the way this is going to work out is, on one side, when we cross multiply, we're going to have 293 times V2, and that's going to equal 600, which is the initial volume, times 333, which is the final temperature. So the first thing we want to do is multiply 600 by 333. Excuse me while I do that in the background. This makes for fascinating viewing, especially when you type it into your calculator wrong. So that's going to give us 199,000 800 on one side, 293 times V2 on the other. So now that we have two numbers to work with, we're going to divide both sides by 293. I'm afraid I haven't left myself enough room to put the answer in here, but I will write the answer up above. And when we divide 199,800 by 293, and I would recommend writing all this out as you go. It's easier to keep track of the numbers that way. So V2, which I'm going to write in a different color up here, V2 is equal to, and I'm going to round this to 3 sig figs here, 682 milliliters. So, to check our work, we're going to make sure first that the answer makes sense. And the answer makes sense if it obeys Charles' law. What we said Charles' law was that as the temperature increases, the volume will also decrease, increase rather. Basically, gases expand as you heat them. That makes sort of intuitive sense. And so we see that when we increase the temperature, what looks like tripling the temperature, but in Kelvin it's actually a pretty small increase, the volume actually increases by a relatively small amount as well. So as long as you remember to put these temperatures in Kelvin, you're going to get some good, reliable answers here, and I hope that this short video on Charles' Law was helpful. Thanks.